Yes, dear students, in this video we are going to discuss antenna theorems. So there are three important theorems out there which use the relationship between transmitting antenna and receiving antenna. So the properties of transmitting antenna, okay, and the properties, the basic antenna properties such as the directional property, impedance property, generally are not identical in the case of transmitting and receiving conditions. So it is quite difficult to compute the properties, but this antenna, you will prove that an antenna, for example, let us see what this could be good antenna. The first one is equality of directional patterns. Equality of directional patterns. Second one is equality of valence, valence, transmitting and receiving antenna impedance. And third one is equality of effectiveness. Equality of effective. Yeah, so these are the theorems. The first one is equality of direction. Second one is equality of transmitting and receiving antenna impedance. And third one is equality of effectiveness. Means, for example, let us take an antenna. Okay, so this antenna can be used both for transmitting purpose as well as receiving purpose. Okay, so whenever this antenna is using transmitting purpose, whenever this antenna is used for receiving purpose, the radiation pattern of both the transmitting and receiving antenna should be same. Okay, similarly, so the impedance, whatever the impedance is antenna, whenever it is used as transmitting antenna, whatever the impedance that is possessed by that antenna should be same as the impedance whenever it is used as receiving antenna. Similarly, for example, whenever this antenna is using as a transmitting antenna, if the effective height is 0.65, in the receiving side also, the effective height should be 0.65. 0.65. Okay, so let us discuss one by one. Let us discuss one by one. Let us come to the first one. The first one is equality of first one. Equality of directional patterns. Directional patterns. Equality of directional patterns. Okay, so coming to the statement, the directional patterns, the directional patterns of an antenna, of an antenna as a receiving antenna, as a receiving antenna is identical to the top, to that when used as transmitting antenna, when used as transmitting antenna. So this is the state. Okay, so means the directional pattern of an antenna as a receiving antenna is identical to that when used as transmitting antenna. So means, for example, if you are using the transmit antenna, this is the radiation pattern in uptake. The same antenna if we use for receiving purpose, then also the radiation pattern should be same. Okay. So how will you prove this? Okay, how will you prove this? Okay, so the proof for this is like this. Okay, So let us consider a test antenna here. Okay. So the voltage is applied to it. Okay, let us consider a small dipole antenna. Okay, so this is my test antenna. This is my small dipole antenna. Okay, so to measure the direction pattern of the transmitting antenna, so the test antenna. So the test antenna is kept at the center of very large sphere, center of very large sphere. This is the large sphere, and a small dipole antenna is moved along the surface of the sphere. Okay, as shown in this figure, the small dipole antenna is moved at the surface of the sphere. Okay, now a voltage V is connected to the test antenna. The voltage V is connected to the test antenna. Okay, placed at the center of the imaginary sphere, and the current I flowing in the small dipole antenna, sharp dipole, is measured using ammeter at different positions. Okay, so ammeter at different positions. Okay, so the current is the measure of electrical field at different positions of the dipole antenna. Okay, so means, so see here at theta is equal to 0 degrees. What is the current? Okay, at theta is equal to 0 degrees. What is the current? Theta is equal to 10 degrees. What is the current rate? Okay, so you are simply rotating your antenna here. Okay, so you will rotate at initially, let us consider A here. After that, you will keep your antenna here. After that, you will rotate like this. At different positions, you are going to measure the currents. Okay. So the current is the measure of electrical field. The current is the measure of electrical field at the different positions of the dipole antenna. Now using the concept of reciprocity theorem, the positions of, now we will interchange this. Okay, in the second case, what we will do? We will interchange this. So we will take this. Okay, here a test antenna will be there. Here short dipole will be there. Here short dipole will be there. Here short dipole. Here test antenna will be there. Okay. Now again, okay, now you will, here also you have to rotate the test antenna and move down this. Okay. Now the positions. Now the same voltage V is applied to the terminals of the small dipole antenna, which is moved along the surface of the sphere. And the current I is also measured in the test antenna, which is located at, here I am keeping my test antenna. Okay, so which is located at the center. Thus, the receiving pattern for the test antenna can be obtained. But according to the reciprocity theorem, for every location of the dipole antenna, the ratio of V to I is same as before, obtained for the test antenna as transmitting end. Okay, so thus the radiation pattern, that is the directional pattern of the receiving antenna. The directional pattern of the receiving antenna is identical to that of transmitting antenna. Okay, so this is the clear. So test antenna is there. Here small dipole will rotate the small dipole. Okay, next we will interchange this. We will bring the short dipole here and test antenna here, and the same thing will rotate. Okay, so whatever the radiation pattern will happen for this, we'll also get the same radiation pattern for this. Hence, we can prove that the radiation pattern of transmitting antenna is same as the direction pattern of receiving antenna. Okay, so this is our first antenna theorem. That is equality of directional pattern. Equality of directional pattern. Okay, now let us go to the second. Let us go to the second one. What is the second one? Our second one is equivalence of transmitting antenna and receiving antenna. That means the impedance of an antenna when it is using the transmitting is same as the impedance when it is used as second one is equality of antenna impedance for both transmitting antenna and receiving. Okay, so we will derive this. Okay, so equality of antenna impedance for both transmitting as well as receiving. And let us see the statement for this. Let us see the statement. Okay, so the statement is like this. The impedance of an isolated antenna, the impedance of an isolated antenna used for transmitting as well as receiving purposes is identical. Okay, so this is the statement of equality of antenna impedance. Okay, so the impedance of isolated antenna used for transmitting as well as receiving purpose is identical. Okay, so let us prove this. Let us prove this. Prove for this. Okay, so consider two antennas, namely A1 and A2. Okay, let us consider they are separated by far distance. Okay, they are widely separated. Okay, as the antenna A2 is located far away from A1, the self-impedance of antenna A1, self-impedance of antenna A1 can be written as self-impedance of A1 is equal to Z1 is equal to V1 by I1, that is equal to Z1. Okay. So this is self-impedance. Okay. So what is this Z11? Z11 is the self-impedance of antenna A1. Okay. When it is acting as a transmitting antenna. Okay. Now when the two antennas are separated widely, okay, so the mutual impedance Z12, the mutual impedance Z12 of the antenna A1, the mutual impedance of antenna A1 can be neglected when A1 is using as transmitting antenna. But the same thing we will not consider when A1 is receiving gas and A1 is acting as a receiving antenna. We cannot, we cannot neglect, we cannot neglect the mutual impedance. The mutual impedance Z1. Okay. So this is the only parameter indicating coupling between the two antennas. So consider the load. Consider the load ZL. Consider the load ZL. Okay, is connected to the antenna A1. Is connected to antenna A1. Used as receiving antenna. Now you are using your antenna A1 as receiving antenna. Okay, so similarly, the coupling between A1 and A2, okay, represented with the help of mutual impedance Z1. Okay, so Z12 indicates the mutual impedance or coupling between antenna A1 and antenna A2, where A2 is transmitting and A1 is receiving. Okay, and the current I2 in the antenna is A2. Okay, the current in antenna 1 is I1 and the current in antenna A2 is I2. Okay, so the equivalent circuit. Okay, so the equivalent circuit of the antenna used as receiving. Okay, is shown here. Now let us see here. Whenever the A1 is acting as receiving antenna, the equivalent circuit Z12 into I2 Z11 connecting the load ZL. Load ZL. Let us consider the current going through this is I1. So this is a loaded condition. This is for loaded condition. Similarly, for let us see for open circuit condition. For open circuit condition, okay, so it is plus minus Z12 into I2. This is Z1. Just consider the current flowing through this is for open circuit condition. Let us do for right for short circuit condition. So plus or minus Z1 to I2 Z1 yes, short circuited crash. I1. This is the for short circuited condition. Okay. So this is for loaded condition. This is for open circuit condition. This is for short circuit condition. Okay. So the generator of the value Z1 to I2. The generator of the value Z12 into I2 can be considered an ideal generator with zero internal impedance, providing constant voltage at its output terminal. At its output terminal. Okay. Now let us come one by one. Okay. So let us for open circuit condition. Next, short circuit condition. Okay. Now let us consider for under open circuit condition. Open circuit condition. Under open circuit condition. So here this is my open circuit condition. So the voltage across the terminal 1 dash is given by, so under open circuit condition, the voltage across the terminal 1 dash can be given by V1C. Okay, so it is nothing but voltage VOC is equal to the open Z12 into I2. Okay, similarly, the short circuit condition, short circuit condition. The short circuit condition, the current flowing through 1 dash. Okay. So the current ISC that is flowing through correct short circuit condition. Okay. So what is the current here? The current flowing through this is equal to the short circuit current flowing through the, it is equal to ISC is equal to Z1 to I2 by Z11. Okay, so Z12 I2 by Z11. Okay, so hence the ratio of VOC, the ratio of VOC to ISC, okay, is as the transfer impedance and is given by VOC by ISC is equal to Z12 I2 by Z12 I2 by Z11, that is equal to Z1. Okay. So under all these three conditions maintained, hence the generator of value Z12 I2 acts as a generator with internal impedance Z11. Okay. Okay. So here also we are getting Z11. Here also we are getting Z11 when A1 is using as transmitting antenna. Similarly, when A1 is using as receiving antenna, here also we are getting Z11. Okay. So hence from this discussion, the effective impedance. Okay. So the antenna impedance whenever it is using as transmitting antenna is same as whenever the same antenna is used for receiving purpose. Receiving purpose. Okay. So let us put the third antenna theorem, that is equality of effective types. Equality of effective lengths. Okay. So very So what is meant by the effective length? For example, let us take a for example, let us take a half wave dipole. Okay, so for example, the radiation pattern is like this. This is my radiation pattern, and so this is my I naught, I zero, this is I z. Okay, so let us consider the L is equal to this is the total. Okay, so here the L effective. Okay, so always the effective length is not equal to the physical size. Okay, so from here to here, I am calling it as L effective. From here to here, I am calling it as L effective. That is L effective. Okay, so if always L effective is less than L, okay, this is physical size. If, for example, if this is the total length, in this only, this portion is effectively used for either transmitting or receiving purpose. Okay, so that is called as effective length. Okay, effective length. Okay, so basically the effective length of an antenna represents the effectiveness of an antenna as a radiator of vector. Represents the effectiveness of an antenna. So the effective length is represents the effectiveness of an antenna as a radiator or reflector. Okay, so the effective length is defined as the length of equivalent linear antenna which has a current I naught, which has a current I naught, which has a current I naught along its length, along its length, all the points radiating the field strength, the direction perpendicular to the length, same as the actual antenna. Okay, so the current I naught is the current at the antenna terminal. The current I naught is the current at the antenna terminals. Okay, so for the transmitting antenna, so for the transmitting antenna, L effective, okay, transmitting antenna is equal to 1 by I naught into integration of L by 2 to L by 2 plus L by 2 to minus L by 2. So total length is L. From here to here it is L by 2. From here to here it is L by 2. So this is positive side. This is negative side. I have Z into dz. I have Z into dz. Similarly, for the receiving end, the effective length can be defined as the ratio of the effective length can be defined as the ratio of open circuit voltage developed at the antenna terminals to the given received field strength to the given received L effective is equal to. So generally, what is the formula for electrical field? Electrical field formula is what are the units of electrical field? Volts per meter or length. Okay, from this L is equal to V by E. So what is the effective formula for the L? Is the open circuit voltage to the developed at the antenna terminals to the given received field strength. Okay, so the other formula for L effective is the ratio of from this formula. Okay, so from this formula it is the ratio of open circuit voltage developed at the antenna to the given field strength. The given field strength. Okay, so therefore L effective of receiving. Okay, so L effective of receiving. L effective of receiving antenna is equal to minus VOC by, okay, minus VOC by, okay. So to show the equality of transmitting and receiving effective antenna, let us apply the reciprocity theorem. Let us consider the transmitting antenna. Let us consider the transmitting antenna at the let us consider the supply voltage is applied. Okay, so this is my radiation pattern. Okay, here, so this is terminal 1, this is terminal 2. Okay, let us consider here a small portion dz. Okay, from here to here, let us consider a small portion dz. Okay, so the effective length from here to here, that is I'm calling it as z. Okay, so this is the physical length. H is equal to L by 2. This is physical length, that is effective length. Okay, so first consider an antenna as the transmitting antenna. This is transmitting antenna. Okay, so let ZA be the antenna impedance measured at antenna terminals. Okay, so ZA is the antenna impedance measured at antenna terminals. Okay, assuming that the voltage V, assuming that you are applying the voltage V at the antenna terminals, then the current produced at the antenna terminals is given as here transmitting antenna I naught is equal to V by ZA. I naught, the current produced at this antenna terminals I naught is equal to V by ZA. I naught is equal to V by ZA. Okay. So similarly, the current at any point Z along the IZ, okay, it's called as prime situation. It's called as prime situation. It's called as prime situation. Okay, now consider the same antenna for receiving. Okay, now consider the same antenna for receiving. Okay, now consider the same antenna for receiving. Okay, so see here, let's consider for receiving. Let's consider here EZ is the electromagnetic field applied on DZ. Okay, so this is for receiving. This is for receiving antenna. Okay, so now consider the same antenna at the receiving antenna. Okay, as shown in this figure. Okay, the same antenna now I am using as receiving antenna. Okay, so consider the electromagnetic field EZ. Consider the electromagnetic field EZ. Okay, is incidental on it. Okay, so this induced voltage. Okay, so what is the expression? This induces a voltage that is Ez into dz in the element dz. Okay, so as the induced voltage is independent of the current through the antenna, it can be indicated as an ideal generator of voltage Ez into dz in series. Okay, in series. Okay, so when the antenna terminal 1 are short circuited. Okay, so the ideal generator produces DS. Okay, dou of ISC at their situation. This is called as double prime. This is called as double prime situation. Okay, so according to the reciprocity theorem, V by IZ is equal to EZ into dz by DISC. Okay, so from this DISC is equal to DISC is equal to EZ into EZ by V into IZ. V into IZ. The next, this is according to reciprocity theorem. Reciprocity theorem. Next, according to superposition theorem, the total short circuit current at the antenna terminals. Okay, it is the sum of the currents produced. It is the sum of the currents produced by all the differential voltages along entire antenna length. Along entire antenna length. Hence, we can write it as. So hence we can write it as ISC is equal to, okay, so 1 by V integral of Z IZ DZ. Okay, so according to Thevenin's theorem, the open circuit voltage at the antenna terminal is given as VOC is equal to minus ISC into ZA. Therefore, VOC is equal to minus ZA by V integral of. So ISC form is this integration of EZ into IZ into DZ. Therefore, VOC is equal to minus 1 by I naught into integration of EZ into IZ into DZ. Okay, IZ into DZ. Okay, so the negative side in this equation represents the conventional current polarities. Okay, so for constant incident voltage or constant incident field, that is A of Z is equal EA of Z. Okay, along the length of the antenna, we can write it as VOC is equal to minus EZ by I naught into integration of IZ DZ. Therefore, minus VOC by EZ is equal to 1 by I naught into integration of IZ into DZ. Okay, same thing. Here also the same expression. Okay, so here also we have got the same expression. Okay, so this one. Okay. Okay. So it is clear that effective length of antenna used for receiving purpose. Effective length of the antenna for receiving purpose is equal to the effective length if it is used for transmitting and antenna purpose. Transmitting antenna purpose. Transmitting antenna purpose.